Oh, hello, hello, search fans. Well, at least I hope you're search fans because I'm Nick Chow, and I'm going to talk to you today about vector search. So, the three things we're going to cover today. First of all, why vector search? I'm sure you've all heard a bit about it in various names. ML, AI, vector search, it's really kind of popped up, and I want to kind of talk through some of the concrete reasonings around just why it's so important now. Why is it such a step function improvement to search? The second thing I want to talk about, vector similarity. And we're actually going to go through kind of an intuitive level overview of how vector search actually works. And then finally, we're actually going to walk through the steps of implementing vector search in Elastic. So I want to start with a little story. I was talking to a friend of mine, and she was telling me about how her mom had met Leonard Cohen in Greece. So I said, oh, Greece like the musical? And she said, no, the other Greece. And I don't know how my mind got there, but oh, Greece like the substance? And she just looked at me like I was from another planet, because of course she meant Greece, the country. It's kind of a silly story, but the reason I bring it up is because our users' search expectations have evolved. That gap between what someone says, what someone means, and the answer that they're looking for is closing. And if we don't meet them there, if we don't meet that expectation, your users are going to look at you like my friend looked at me. So concretely, what are some of those changes in user expectations? The first one is an actual expectation for semantic kind of semantic search, semantic interaction. So if a user, for example, types in an account, I think it's totally reasonable for them to expect that you would cover transaction history or user profile as well as account. They expect the same thing. Input flexibility. We've talked about chat already, being able to interact through your search, being able to find things through chat, but also things like image search. So being able to take a picture of a product and then actually kind of finding similar like-minded products. Or even just natural language queries, just being able to ask a computer in the same way that you would ask a normal human being. Finally, or thirdly, context and domain specificity. Words mean different things in different contexts, and it's up to us to make sure that we reflect that in our search. So back to accounts. Someone's account means a very different thing if you're in finance versus if you're in, say, the legal or law enforcement profession. And finally, precision. There's that joke about the best place to hide a secret is in the second page of your search results. Users are backing that up. They're expecting more and more. So it's not even just the second page now. It's like the 10th, third, first result. If that first result doesn't matter, if that first result isn't germane, your users are going to start kind of looking at you askew. So I want to start off with a concrete example of kind of the difference between vector search and term-based search or regular token search. So if we have a document talking about our connection speed requirements. If a user types in, how fast should my internet be? None of those words match. They're probably not going to find that document unless you take the time to add a bunch of synonyms, but there's a limit to that. There's only so many synonyms you can add before it just starts washing away and doesn't matter at all. So vector search helps kind of bridge that gap, helps bring us there. So let's talk a little bit about that concrete, like how vector search actually works, kind of an intuitive overview with it. I'm going to try to spare too many gory details. I'm going to try to keep it intuitive, but just hang on. So let's kind of take that existing example. At a very, very high level, vector search takes your documents, encodes them into a vector, hence the term, and then on the opposite side, takes a query, takes a thing that your users are searching for, and encodes that into a vector as well. We then find kind of in that multidimensional space the closest documents to the one that your user kind of has generated, is looking for. And that kind of finds the most like documents in terms of semantic similarity. So let's dive into kind of some more concrete details around that. first and foremost is the actual process of taking your document and encoding that into a vector. And that's done through a model, a machine learning model. Machine learning models are generated by taking a bunch of training sets or training data and using it to develop a kind of like a computer understanding of a universe, a computer understanding of what words mean and where they fit in and the context of meaning and understanding. There's a bunch of different techniques to do this, like convolutional neural networks. That part's not important. The important thing is that models are super unique to that training set, to that data. And once it kind of takes your documents, it's able to encode its understanding of that document into a vector. So what is a vector? A vector is just a set of numbers. It's a set of numbers in a fancy square bracket if you're looking at it from a math point of view. But really, we see this in everyday life. So for example, if you've ever asked for someone's location and they've given you a lat long, a latitude and longitude, that is a two-dimensional vector. That is two numbers which tells you exactly where on this planet someone is. Now imagine instead of on this planet, it's actually multiple dimensions and it tells us where they fit in kind of an understanding of our like universal understanding of things. So here's an example. We've got a cartoon elk on one side and a realistic elk on the other. So if we start by drawing one dimension, that's one number, the first dimension, on one side we've got cartoon, and then on the other side we've got realistic. Oop, that's the wrong way. From that, let's add another dimension, a second dimension. In this case, it's mammalian and avian. So we've gone from just being able to talk about elk to being able to talk about, well, we've got elk, we've got birds as well, in this case, owls. And we can kind of apply the same dimensional kind of differences, so cartoon owl, realistic owl. Now imagine you can kind of plot a whole bunch of different documents, or in this case, images, on those same axes, on those same dimensions. Now, of course, in this case, there's going to be more than just two dimensions. There's going to be multiple. There's going to be many. It could be, I don't know, animals with horns versus animals you'd find in a farm or whatever it is. At this point, it is worth mentioning that machine learning models don't work so cut and dry. They don't work so cleanly. Its understanding is developed in kind of more of like statistical sense. So those dimensions don't actually mean anything to a human. They're just there to encode that knowledge. So let's put all of this together. On one side, we have our documents. We've embedded in all of those a vector for each one. Each one of those gets a point in our multidimensional space, which kind of tells us where they fit in terms of our universe of understanding. On the other side, we have a query. We have what the user is asking. That's also encoded into a vector, into a point of that universe of understanding. So the kind of like next neat trick here is actually taking that point and finding the closest other points to it, the other closest documents to it, because those are the most likely to be similar. And so we do that in a variety of ways, a dot product, cosine similarity, or just boring old Euclidean distance. But the important thing is that we do compute the distance and find the closest ones. So back to our elk bird example. If we have, for example, as our search term, cartoon elk on a desk, then you can kind of see it's kind of faded back there. But you can see that the closest results are, blue cartoon elk, purple cartoon elk, maybe an elk with wings. That's also a cartoon, and so on. I think the other thing that's worth mentioning here is that what you get returned isn't necessarily just ordered, but can also include distance. So you could say, well, those two colored elks are like much closer, but the elk with wings is going to be further apart. I think the other important thing here is so far we've been talking about precise distances, and precision comes at a cost. So going from kind of laboratory conditions to more real world ones where we have user expectations like query response time, or kind of our use case conditions, like having millions and millions of documents, being able to have something that's fast and scalable, requires a few compromises, requires a few kind of hedges. And so one of the things that we've done to address that is a technique called HNSW, Hierarchical Navigable Small Worlds. So that works if you can imagine all of our documents, all of our vectors, as a graph or a dot with connected nodes to each other. Add a layer on top of that, with less of those nodes, with a subset of those nodes. And then a layer on top of that with even less and less and less. And so when you search now, you start at the very top where there's very few nodes, and your search space is much smaller. From there, when you find the closest node, you drop down a layer, and now you don't have to search the entire space. You only have to search the stuff that's closest to it. And you can use that to drop further and further down until you've kind of come to your closest documents. It strikes a really good balance between having something that's fast and something that kind of is performant, and also something that works at scale to millions and millions of documents. Okay, so we've talked a little bit about how vector search works. Now let's talk about how we can actually concretely apply it using Elastic. So you need 4 things to make this work. The first one is a use case. A lot of times folks will come to us and say, essentially, can you help wave that magic ML wand to make my search better? And the answer is no, we can't. You have to have a little bit of a kind of a more thoughtful or reasoned out approach to it. You need to know a little bit more about your use case. And that means your data, the structure that your data takes, and exactly how you want vector search to enrich what you're working on, to enrich your search results. The second thing is an Elastic Cloud account, a place to actually host and run your machine learning nodes. GovCloud is a great place to do that. You don't have to worry about any sort of like operational stuff, like scaling ML nodes and deploying them and all that. Elastic Cloud and GovCloud help you take care of that. The third thing is a machine learning model. And this is the juicy bit. This is kind of the interesting thing, because this is choosing the mathematical representation of your universe, of the world that best reflects your domain, your use case, what your users are thinking and looking about. That gets tricky and also gets super fun. That's probably why I'm not invited to a lot of dinner parties anymore. But I think it's super fun. The last thing there is your actual application. How do your users interact with that query, with that search? How do you generate that search? What is it that they're looking for? So at a very, very high level, let's kind of go through this. First and foremost is that model, picking that model and the thing you are looking for, that understanding of the universe. The second thing that we need to do is actually ingest our documents, getting all of our documents into Elastic Cloud, into Elasticsearch, and making sure that they have their vectors embedded. And then the third thing is actually taking a user query and putting that together, issuing a query, actually issuing a search. So let's talk about first the model. If you don't have a large data science team or machine learning scientists, that's okay. There are models that are openly available on places like Hugging Face. There's more and more, kind of like the time is right now. There's more and more of these appearing, and it's just getting better and better. Of course, they tend to be much more general. You'll find some with specific domains or use cases, but they do tend to be more general. If you do have a data science team, that's awesome, because you will find that the best kind of like results with vector search come from having that like fine tuning or additional layer of training on top of your models. That really, really helps. In fact, that's so important that one of the things that we focused on when we were building machine learning for Elasticsearch is the ability to interoperate models, is the ability to swap back and forth between models. Because not only is it super important that you pick one that's close to your use case, but it's also really important that you be able to evolve your model. As you learn more, as you gather more data, that you're able to change and update your model really quickly. You load all of that into your machine learning clusters with a tool called Eland. It's kind of just an easy way to take your machine learning model and load it up into your machine learning nodes. And then finally, you manage your models. We've put a lot of time and thought into making that really easy to do. On Kibana, it's possible to just dive right in there, select your models, select the versions you want, and kind of also look at kind of operator helpful things like whether they're running, how many errors they've had, things like that. Next, data ingestion and embedding. So actually getting our documents in. First, there's all the fields that we know and love with normal search. So things like title, things like description, that all kind of gets through, bog standard. The magic here comes from actually encoding the fields that we want to be vectorized. And so there's a really kind of like a segmented way to do that using Elastic, and that's through something called ingest pipelines or inference pipelines. Ingest pipelines are a really easy way to reason about what changes your documents take while they're being ingested before they come to their final state, their final form in Elasticsearch. And so one of those are inference pipelines or machine learning models and running it through a machine learning model. So same thing, we've put a lot of effort into making that really easy to do and really accessible in Kibana. So you just add one click and do so. So now you've got all your documents encoded. They've each got their vector embedding. Your documents are good to go. The third and final step is actually sending a vector query. Is taking that user taking that user query, that user input, and then the first thing is actually running it through that same model. Of course, it does have to be the same model. If it's a different one, then you just get some other point that's way over there or isn't even compatible because you've, of course, got to run it through the same understanding of the universe. Once you've got that vector, you add it to _search. I want to talk about this for a second because this part's really neat. You can do vector search through the _search endpoint, which is kind of exciting for a couple of ways, one of which I'll talk about later, but one of which is developer ergonomics. It's just way easier to be able to use the same _search endpoint without having to worry about swapping your clients and API keys and things like that. You're just able to kind of like change and append your Elasticsearch query. So the actual way that we perform that query in Elasticsearch is with a new clause called the KNN clause. KNN stands for K nearest neighbors, where K is a user-definable number of the number of documents that you want to return. So once again, you've got your vector. How many of those closest documents do you want to return? That also includes, at the bottom there, you'll see filter. That also includes kind of those like search table stakes are nice to have. Like if you know documents that you don't want to have included, you can kind of exclude them right away there using a filter. We talked about that. The other really nice thing about including that in _search is that you can combine it with the BM25F that we know and love. So hybrid scoring, or an ensemble technique, is when you blend or combine information retrieval models, and benchmarks generally show that you get way better results when you do that, even with a fine-tuned model. So you take kind of, good old BM25, that's the text search that we all dig at Elasticsearch here, and we can combine that with that vector similarity score. We can combine that together to produce a much better set of results. And we do that with something called linear combination, which _search essentially takes care of for you under the hood. All you need to worry about here are the boosts, which you can see over there, kind of change the weightings between those two scores. It's going to be really different per use case. It's really going to kind of vary depending on your use case and kind of how you're scoring relevance. So this kind of allows you to tweak it as you need to. So there you have it. That is a brief overview of what vector search is and how it works and how you can make it work in Elastic. The last thing I want to talk about are some examples of real-life customer projects that Elastic, that we've seen in our time here of folks using vector search. So the first one is product similarity. Here we talk about, can I can you find me a black V-neck t-shirt that looks like this one? But that document similarity applies just as well to things like patent search, which was another project that we learned about recently. And there, vector search becomes particularly exciting for something like patent search because you're no longer relying on the searcher to hit those terms of art, to hit like those specific keyword terms. It's a really kind of like exciting way to encode and just like retrieve kind of like a very specific use case or domain. The next one there is technical support. So if you have folks asking questions, kind of any like either public or customer support facing knowledge-based questions, that's another really big one and a really important one, and one where natural language understanding really kind of comes into play, the ability to query like you would a human. Because, for example, knowing the difference between someone asking, how do I renew my plan and when do I renew my plan could be the difference between a quick search or like really long customer support call. The third one there is domain-specific knowledge. This is where having those fine-tuned models really, really shine. If you are in a specific field with really specific terms and concepts, then vector search might work really well for you there. In particular, if that intersects, if that crosses with public search, where the average layperson might not be as familiar with those terms. Finally, reacting to user sentiment. This is kind of more of NLP, like natural language processing enrichment kind of thing. But I think it's really an important one or useful one to point out. And that's the ability to take a tranche of text, a body of text, and tell what the sentiment is behind it, to be able to say that it was positive or negative or aggressive or what. And that's useful in so many ways. You can flag ones that are problematic. You can boost ones that make sense to you. You can really highlight kind of really, the sentiment that you're looking for or not looking for. So that has been a whirlwind tour. Thank you all very much for coming along on the ride with me. If you're as excited about vector search now as I am, you can come check us out in a couple ways. One, come say hi to us on Elastic Cloud. It's a really easy place to get started. I know it says 14 days free trial here, but I believe on GovCloud it's 30. The second way is with resources. We've got a ton of resources, blog posts, webinars, guides. We've got a ton of resources to help you get started. And third, come say hi to us. We've got a booth out in the other room called Enterprise Search and Geospatial. Come talk to your rep. Come find me in the hall. Yeah, we're more than happy to chat about vector search. We've had a ton of improvements that have come out over the past little while. There's a ton more coming, so please stay tuned. Thank you all, and yeah, happy searching.